Hello everybody and welcome to the video on sections 5.1 and 5.2. In this video we begin our investigation of a new topic, and that new topic is graph theory. So chapters 5 and 6 are both dedicated to the study of graph theory. The reason we are studying graph theory is because it's a very powerful tool to solve all sorts of real-world problems. And the real-world problems that we will be investigating in Chapter 5 are called street routing problems, and in Chapter 6 we will study what are known as traveling salesman problems. So essentially, both of these kinds of problems boil down to: imagine that you are a delivery service, or maybe a patrolling service, like a security patrol service, or any sort of delivery service, mail delivery, things like this. Then as you perform your route, as you go through your delivery route or you walk your patrol route or whatever, generally you are trying to minimize something. So you might want to minimize the amount of time it takes you to do this, to walk your route. You might want to minimize the amount of gas you use if you're driving a delivery truck. You might want to minimize the amount of distance it takes you. And all of these three things might be distinct. But at the very least, as you move through the world, as you're delivering things, or as you're patrolling a neighborhood or whatever, as a security guard, as you're moving through the world, you want to minimize the cost of something, the cost of time or distance or literal money cost through gas money, whatever. So that's what chapters 5 and 6 are about. And to investigate these problems of moving around, we will use a tool called a graph. And let me warn you ahead of time that graph is a loaded term in math. If I ask you to picture a graph, you probably will think of like a bar graph, perhaps. Depending on how close you are to your high school math education, you might think of a graph of a parabola or something, the graph of a function. These graphs are entirely different. You probably have not seen this kind of graph before. So it's something new. So in this video, we're going to start an introduction to graph theory. And section 5.2 is what we will focus on. Section 5.1 just sets up the kinds of problems that we will be dealing with. It is a short section and has no homework. So we will briefly spend time in section 5.1 investigating the kinds of problems we will solve. And then 5.2, we actually introduce what a graph is and notation and terminology and things like this. So let's start with section 5.1 to give you some motivation for the kinds of problems we will solve. So the story of graph theory begins in the 1700s in Königsberg in Eastern Europe. At the time, Königsberg was divided by a river into 4 separate sections, and they were connected to one another by 7 bridges. So let's just take a look at this. This is a map of Königsberg. Here are the 7 bridges. So let's count 3, 6, 7. Okay. So the 7 bridges connecting the 4 different land masses. While visiting Königsberg, the mathematician Euler, and if you haven't heard that name before, he's a top 5 mathematician of all time. So he was a transcendent genius. So Euler was told of an innocent little puzzle of disarming simplicity. Is it possible for a person to take a walk around town in such a way that each of the 7 bridges is crossed once and only once? So just imagine for a second that these bridges are lined with street vendors, and your job is to make deliveries to the vendors along each bridge. So you are going to cross this bridge, and as you cross, you're making deliveries to people along the bridge. But there are vendors on this bridge and on this bridge and on all the other 4. So along all 7 bridges are vendors that you have to make deliveries to. So if you're going to do this, if you're going to make these deliveries, what you would like, let's just say you're based out of this building right here, wherever. You'd like a way to walk across all 7 bridges once and only once, because why retrace your steps, right? That's inefficient. You would like a way to start and end at this building right here and walk each bridge once and only once without retracing your steps, making your deliveries along the way. So maybe you start at this building and then you cross this bridge, make your deliveries, and then go down here, and then maybe go over this one, and then over this one, and then maybe this one, and then this one. Oh, but now So you've covered these 6 bridges, but you haven't been to this one yet. So to get from right here down to this bridge to make your deliveries, you're going to have to retrace your steps somewhere. You're going to have to like cross this bridge to come down and then to get back over. Or maybe you have to cross this one and then come down and cross, and then you have to cross again. So basically, you want to find a way to walk these bridges without walking any of them twice. So the question is, can you do that? If you are this delivery person that needs to make deliveries along these bridges, so you have to cross them, is there a way to walk so that you cross each bridge exactly once? So once and only once. So Euler solved this problem, but what he actually did was he laid a very broad theoretical framework for solving all sorts of other problems. And that framework that he built is called graph theory. So at the time, they didn't call it graph theory. They called it like the geometry of location, but we call it graph theory now. And his ideas developed into what we now know as graph theory. And by the way, this is a class you would take in like graduate school, so it's like a really well-developed field. So the theme of this chapter is the question of how to create efficient routes for the delivery of goods and services. So think of mail delivery, garbage collection is a big one, right? Garbage companies are always wondering, is there a more efficient way to route our trucks? Police patrols, newspaper deliveries, etc., right? These types of management science problems are known as Euler circuit problems for reasons that will become clear as we move throughout the chapter. So what is a routing problem? To put it in the most general way, routing problems are concerned with finding ways to route the delivery of goods and or services to an assortment of destinations. The goods or services in question can be anything, really. And the delivery destinations can be homes, distribution centers, terminals, whatever. So it's just a catch-all term for anything like this. There are 2 basic questions to ask. The existence question. Can we find a route like what we want? So let me go back to this picture here. You're based out of this building right here. You want to walk along each bridge in the city once and only once and return to where you started. So the first question you might ask is it possible to do that? That's just a yes or no question. Is it possible? That's an existence question. For most routing problems, the existence question will be easy to answer once we develop the tools of this chapter, and the answer takes the form of a simple yes or no. However, once you know that there is such a route, then there's a very natural follow-up question, and that is, okay, well, what is it? And if there are multiple optimal routes, like what should I take, So these are the kinds of questions we will ask. Is there the kind of route that I want? Yes or no? If the answer is yes, okay, then tell me what that route is, right? Because just telling me yes doesn't actually tell me where to walk. Once I know I can walk an optimal route, please tell me where to walk. The common thread in all of these problems is what we might call, for lack of a better term, the exhaustion requirement. The requirement that the route must wind its way through everywhere. So in this bridges problem, you have to walk every bridge. So in an Euler circuit problem, every single one of the streets or bridges or lanes or whatever within a defined area must be covered by the route. And we will refer to these types of routes as exhaustive routes. So here's our first example. After a rash of burglaries, a security guard is hired to patrol the streets of a neighborhood. The security guard's assignment is to make an exhaustive patrol on foot through the entire neighborhood. And obviously, he doesn't want to walk any more than what is necessary. So he's going to park his car right down here. And he must walk this entire neighborhood, which means he has to walk this whole stretch of road at some point, this entire stretch of road at some point, right? This block he has to walk, this block he has to walk, etc. You get the idea. And of course, suppose that he walks this block. Well, he'd prefer not to walk it again because that's not efficient. Once he's already walked this block, he would like to be able to now return to his car and maybe start his route over or something, but he would like to walk efficiently. So if he's just being hired to patrol the neighborhood once, he would like to minimize his time and not have to retrace his steps ever. So the security guard has two questions to ask. Is it possible to start and end at my car at S, which again is just right here where he parks? Is it possible, oops, I went the wrong way. Is it possible to start and end at S, cover every block of the neighborhood, and pass through each block just once? So exactly once. Well, that's a yes or no question, right? Is it possible? Well, yes or no, right? Well, if the answer is yes, okay, can you tell me what that route is? If the answer is no, if some of the blocks will have to be covered more than once, then okay, I'm going to have to retrace my steps some, but can you please still try to minimize the amount of walking I do? So maybe it's the case that you can find him a route where he has to walk this block twice. That's fine. Okay, maybe that's the best you can do. That's still better than making him do like walk here, walk back, walk here, walk back, walk here, walk back, right? I mean, here's another route that I'm describing that's just ridiculously inefficient. So these are the kinds of questions we're interested in. How do I minimize the amount of walking I do if I'm the security guard? I would like to walk each block exactly once, but if that's not possible, then just find me a route where I minimize the amount of walking I do. So here's another example. It's the same basic thing. You have a guy based out of the post office, and he wants to make deliveries along each side of the road now. So the security guard only has to walk a block once, but the postman must walk each block twice because he has to go up, down, right? The right-hand side of the street, then the left-hand side. Up, down, and he has to do it on all of these blocks that have stuff on either side. So he will have to retrace his steps in some sense, but in this case, you can think of each sidewalk as being a separate route. So he's going to walk on this side of the street and then this side of the street, and then he'd prefer not to have to walk this street again after he does this. So here the post office is fixed, so the mail carrier has no choice but to start and end where the post office is. The security guard could presumably park his car somewhere else. So if we couldn't find him a route at S, starting at S, maybe he could have parked like right here and he could do better. Okay, so yeah, the mail carrier wants to find an optimal route that would allow her to cover the neighborhood with the least amount of walking. Okay, so basically here we have two figures. One shows the city of Königsberg and its 7 bridges, and the next shows a modernized version of the very same layout. So we open the chapter with this question: can a walker take a stroll and cross each of the 7 bridges without crossing any of them more than once? So here's sort of a more modernized version where the buildings have been taken out so we can just see the necessary information. This is a more, Okay, yeah, so basically we just remove all of the context just to get down to what we want here with this figure. Okay, here's a last example, I think, or second to last example for 5.1. Think about a picture like this. So these are the bridges of Madison County. There are what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them. So imagine that you, again, are making deliveries along each bridge, or I think the exact example here is that you want to, take pictures of all of them, and so you have to cross them all to take pictures of them. So again, let's just say that your hotel is right here on this island. Is it possible, as the photographer, to find a path so that you cross each bridge exactly once? So maybe if you're right here at A, you can go over, and then maybe down, and over, over, over. Oops, I already retraced my steps if I do that. So, there's 11 bridges, so you have to be careful with this. So over, over, down, maybe this way, and then down. So I get stuck again. So these questions are open, right? Like, how do we do this? So the photographer needs to drive across each bridge once for the photo shoot. Moreover, since there's a $25 toll every time an out-of-town visitor drives across the bridge, he, of course, wants to minimize the cost of his trip and to recross a bridge only if it is necessary. So again, the question for you is, well, if you're this photographer, what do? You could be an idiot and you could go like over, back, and now you got these 2 bridges covered, and then over, back. If you have some imagination, you can think of some really stupid ways the photographer could plan his route, right? But we're not looking for stupid ways to plan the route. We're looking for the best way. Okay, the very last example from 5.1 is just something like this. Imagine you're a kid who wants to trace these figures, and so you want to like put your pencil down and like trace literally like this with my mouse, right? And imagine that you want to do this tracing so that you don't lift up your pencil. I think that's the restriction here. Yeah, without lifting the pencil or retracing any of the lines. That's the restriction. So which of these figures has that property that I could plop my pencil down and trace it without lifting my pencil or retracing something? So this one here, can we do it? Let's try. So got those three. And then, man, can we? So like this. I think I did that without cheating. Okay, you'll have to check me out on that path I did with my mouse. But anyway, so this one we can. This one I don't think we can. And this one I don't think you can either. Okay, but the question is, well, how would you know that? How would you know which things you could trace without cheating, without lifting your pencil or retracing something? So it's hard to know unless you have tools to answer a question like that. So that's section 5.1. Those are the kinds of questions that we will answer. And how will we answer questions like that? Well, we're going to use the tool that Euler built back in the 1700s. We're going to use graphs. So Euler circuit problems can all be solved by means of a single unifying mathematical concept, and it's the concept of a graph. The most common way to describe a graph is with a picture. Everybody likes pictures. The basic elements of such a picture are a set of dots, which are called the vertices, and a collection of lines, which are called the edges. So that really is all there is to it. There's just dots with lines connecting them. So you might think, that sounds stupid. I mean, what are you going to get out of that? So here's a picture of such a thing, okay? It's just dots with lines connecting them. So you might think, that's a trivial concept, right? Dots with lines. But it actually turns out not to be a trivial concept. It turns out we can solve all sorts of problems by thinking about the problems as a graph. So here's an example. This is a graph. It has 6 vertices, 6 dots. You can call them A, B, C, D, and F. You can always give them names if you want. Each edge can be described by listing the pair of vertices that are connected by the edge. So in this case, there's an edge between A and B, and so you can write it like this, AB. There's an edge from B to itself, so you can call that BB. There's an edge from D to C, etc. There are multiple ones from D to C. So the most common misunderstanding that students have at this point, when I'm just showing them a picture of a graph, is they think that like right here, they think that's a vertex. They think that's a dot. They think that anytime an edge crosses another edge, it must be a vertex. But that's not true. Vertices only exist where I've labeled them to exist. So imagine that this graph represents something like, what would this represent? Like a family relationship, like A is related to B, and for some stupid reason, B is shown as being related to himself, and B is related to C, right? If that's what this graph represents, then the fact that these lines cross right here doesn't mean anything, right? A is related to D, E is related to B, and that's it. The crossing here makes no difference in that information. So let's notice a few things about the edges. It's possible to loop. It's possible to go from a vertex back to itself. Okay, that's fine. It's possible for two edges to connect the same pair of vertices. So between D and C, there are multiple edges. That's okay. That situation is referred to as multiple edges. Sometimes edges cross each other, but as I just pointed out, the crossings themselves are not vertices. And the example the slide gives here is exactly what I just said earlier. Edges don't have a direction. So there's no right or wrong order in which to write the edges. You can describe this edge right here as AB or BA. It doesn't matter. There's no like flow to this picture here. Okay, so a convenient way to describe the vertices and edges of a graph is by using the notation of sets. So we'll describe the vertex set like this. So this is just fancy language for saying we're going to list the vertices. So we've listed all 6 of them, and then we can list the edges too. There are what? 1, 2, 3, 4, 5, 6, 7, 8 edges, and they list them all here. So AB is this edge, AD is this edge, BB is this loop, BC is this edge, etc. Notice that CD appears twice because there are 2 edges connecting C and D. Let's look at an example now of actually what I just said a second ago, a relationship graph. So imagine that as part of a sociology study, we want to describe the network of friendships that develops among a group of students through their Facebook sites. We can illustrate this very nicely with a graph such as the one in the next figure. So in this figure here, the vertices represent people. So your vertices can, in general, represent whatever you feel like. They can represent delivery sites or cities or people or whatever. So this is a relationship graph. What this means is that Meg, she's friends with Betty, Moose, Jughead, and Ginger. Okay, I didn't make this, so I don't know why like people are named Jughead and Moose in this thing, but whatever. So basically the vertices represent people, and an edge represents a friendship. So we draw an edge between 2 people if and only if they are friends. That's what this is saying here. An edge connecting vertex X to Y means that X and Y are Facebook friends. So this picture here is just a visual representation of a friendship network. So Betty here is sort of the friend winner because she has 5 friends, Meg, Moose, Ginger, Reggie, and Archie. And Veronica is kind of the loser of this picture because she only has 1 friend, just Archie. Okay, so figure 5.8 shows a graph with 4 isolated vertices and no edges. So we won't see graphs like this very often, but sometimes you'll have vertices that aren't connected to anything. And that's okay. So for example, back here, suppose that Veronica had no friends. Then she would just be a vertex off by herself. This edge right here would be gone. So sometimes you'll see that. Not terribly often, but, you know, it is what it is. Okay, so suppose you are given the following information about a graph. The vertex set is 4 vertices, A, D, L, and R. And the edge set is E equals this stuff. So there's an edge from A to D, from A to L, from A to L again, from A to R, from A to R again, from D to L, and then from D to R. Well, where's the picture? Well, you can make one if you want. That's fine, but where should you place the vertices? What should the edges look like? I mean, presumably there are all sorts of pictures you can make, like the edge from A to D. Is it curved or straight? These 2 edges from A to L, are they squiggly or straight? You know, whatever. You can make the graph however you want. It doesn't matter. You know, you're not going to be writing down much for me because you're doing all this online. But in class, I would prefer them not make things so squiggly because it's sort of hard to read. But, you know, these 2 graphs are the same. They represent the same information. So just to confirm that, look, D right here is connected to R, A, and L. And the same is true here. R, A, and L. D is connected to. In this picture here, R and A are connected twice by 2 edges. And that's the case here too. R and A, R and A. So these 2 graphs look a lot different, but they're functionally the same thing. There's no difference. So while they may look totally different, they describe the same vertex set and the same edge set. So they are the same graph. It doesn't matter which one you use. We think of a graph as a picture consisting of dots and lines, but the picture is just a visual representation of a more abstract idea. The idea is that there's a set of objects, represented by vertices, and a relationship between 2 objects, which is represented by the edges. So all that you need to do to describe these 2 things are a vertex set and an edge set. The vertex set tells you the objects you're interested in, and the edge set tells you how they are related. A picture is nice, but not always necessary. Just from the edge set and the vertex set, you know everything you need to know about the graph. Once you have these 2 sets, everything else is just aesthetics. It just depends on how you want to draw your picture. So here's our definition of graph. A graph is a structure consisting of a set of objects, which is the vertex set, and a description of how the objects are related to each other. Relations among objects include the possibility of an object being related to itself, as a loop, or multiple relations between the same pair of objects. So if your objects here are cities, and your edges represent roads, then it's certainly possible that a city has a road from itself to itself. It is certainly possible that between a given pair of cities, there are multiple roads between them. That's all fine. Let's get down to some terminology now. Every branch of mathematics has its own peculiar jargon, and graph theory is no exception to that. So for the rest of this section, for the rest of this video, we'll be dealing with some terminology that we will need in the next, in our case, 2 chapters. We're not going to do chapter 7. We say that 2 vertices in a graph are adjacent if they are joined by an edge. So intuitively, vertices are adjacent if they are next to each other. So A and B in this picture are next to each other. They're connected by an edge. A and F are not adjacent. When you have a loop, you can say that E is adjacent to itself. Right? There's an edge connecting E to E, so E is adjacent to itself. We can also speak of edges being adjacent, and the idea is the same. This edge right here from E to D, that's adjacent to the edge between A and D, from E to E, and from E to B. So an edge is adjacent to another one if they share a vertex, or if they literally just are adjacent, right? However you want to think about it. This definition here is slightly more subtle, but it's extremely important because the degree of a vertex is how we're going to solve street routing problems. The degree of a vertex is the number of edges meeting at that vertex, and loops count twice. So what you have to imagine doing to calculate the degree of a vertex, let's focus on A just for a second. Zoom in on A and draw a tiny little circle around A. So imagine this mouse is drawing out a tiny little circle. How many spokes do you see? So imagine this is a wheel, right? How many spokes do you see in that wheel? Well, there's this little piece here, this little piece here, this little piece here. There are 3 spokes. That means that the degree of A is 3. If you do the same thing for G, you only get 1 spoke, so the degree of G is 1. If you do B, sort of circle, there are 5 spokes, so the degree of B is 5. If you do E, notice there are 4 spokes, right? 1 there, 1 there, 1 there, and then 1 there. So the degree of E is 4. That's what the degree is. Distinguishing vertices with an even degree from vertices with an odd degree is going to be critical when we get to section 5.3, so we make those their own separate definitions now. An even vertex is a vertex with even degree. An odd vertex is a vertex with odd degree. So A, for example, you can say that's odd because its degree is odd. Its degree is 3, and 3 is an odd number. On the other hand, the degree of E was 4. 4 is even, therefore we call E even. Okay, so let's move on to a next bit of terminology. Paths and circuits both describe trips along the edges of a graph. So a path is basically what you think it is. Just imagine that this is a network of streets or something, and you are based out of E, and you want to take a walk. Well, you can walk from E to D, and then from D to A. That's a path. You can walk from E to itself, and then E to B, B to F, and then F to G. That's a path. You know, just any sort of walking tour through a graph is called a path. If you want to do E to D, and then immediately B to C, that's not a path. You're not allowed to teleport. So if you go from E to D, you must now go from D to A. That's your only option. If you go from E to B, you're now allowed to go from B to A, B to C, B to F. You can't just go straight from B to G. So a path is just a sequence of edges that are all adjacent to each other. Okay, the only difference between a path and a circuit is that a circuit is closed, which means that you end where you started. So in this picture here, E to D, D to A, that's a path. That's just a walking trip. It's not a circuit though, because you didn't end where you started. However, if you did like E to D, D to A to B, B to E, That's not only a path, it's also a circuit because you started and ended where you at the same spot. So circuits are paths. Okay, circuits are a specific kind of path. In this context, by a trip, we mean a sequence of adjacent edges with the property that an edge can be traveled just once. So basically, you don't want to be doing things like ping-ponging back and forth between A and B all the time. You generally would kick that out because it's inefficient. The standard way to describe a path or circuit is simply by listing the vertices that you travel. So for example, ABED is a path from A to D. So you can go A, B, E, D. Just list the vertices. The drawback in listing vertices like this is like, suppose somebody said, oh, my path is ABC. Well, going from A to B is fine because there's only one way to do it. But when somebody says, oh, and then I went from B to C, well, there are two ways to do that. So I don't actually know which one of those you took. So sometimes we won't write paths just like this because of this issue here of multiple edges. Okay, when you take a walk like this, the number of edges in that path is called the length. So A to B, B to E, E to D, we walked three edges, and therefore the length of that path is 3. A, B, C, A, D, E is a path of length 5 from A to E, and this path hits vertex A twice, that's fine. No edge is repeated, however. And this path here actually comes across that issue I just said. Like A to B, B to C, well, which one of these do you mean? If somebody writes a path like this and there's ambiguity, they basically mean it doesn't matter. So you can consider this path as being one of two different paths if you want to. You can go like A, B, B to C like this, or A, B, B to C like that. And either way is legitimate. Okay, a few more paths here. So think about something like this. A, B, C, A, B, C, B, A, D. Oh yeah, so we don't want to traverse the same edge twice. That's what it's saying here. So we did A, B twice, and we prefer not to do that. Okay, so you get the idea here. Let's look at another one, B, C, B. So B to C, then C to B is a circuit of length 2. So circuits of length 2 are possible when you have multiple edges like we do. So B to C, C to B, it's implied that you're doing a different edge on each trip here. The EE loop is a circuit of length 1. So you start and end at the same spot. A graph is connected if you can get from any vertex to any other vertex along a path. So basically a connected graph is a graph that comes in a single piece, as this graph does. So if I ask you, is this graph connected? All you have to do is ask yourself, well, can I get from any vertex to any other vertex by walking? And the answer is yes. So consider like H and E. Can you walk from H to E? You certainly can. You can go from H to F, F to B, B to E, right? No problem. And that's true for any two vertices. Given any two vertices, you can always find a path between them. And that's what it means to be connected. But consider a picture like this. This is called a disconnected graph. Because now I could ask you, well, can you get from like G to H? And you'd say, yeah, sure I can. G to F, F to H, that's fine. And then I could say, well, can you get from G to E? And you would say, well, no, I can't. There's no way in this picture to walk from G to E. And since you can find two vertices where you can't walk from one to the other, this graph right here is disconnected, as is this one. A disconnected graph is made up of separate connected components. So a component is simply a connected graph inside of the overall one. So in this overall graph, it's disconnected. You can't get from G to E. But inside of this graph, you have components. This right here is a component. It's a like connected subgraph, as is this. So this graph has two pieces. So if you like, a component is just a piece. So here's one piece, two piece. This graph here has three components. So this is a piece right here. This is another piece. And then the vertex G is isolated. So it's an island unto itself. Okay, Notice that in this figure here, this is the graph we get when we start with this graph right here and just snip out this edge right here. So we just erase the edge from B to F. So notice that. This illustrates how the removal of just one edge from a connected graph can sometimes make the graph disconnected. So notice here, this is a connected graph. When I snip out BF, it's no longer connected. So BF is kind of a special edge like that. So notice that like if I removed this edge from E to B, if I just erase that, that action would not result in a disconnected graph. So if I take out this edge right here from E to B, the resulting graph is still connected. But if I snip out this edge from B to F, the resulting graph is disconnected. That's what it means to be a bridge. So a bridge is simply an edge whose removal disconnects the graph. So you start with something connected. If I now remove this edge, the graph is no longer connected. Okay, just a couple more bits of terminology and we will be done. I should have warned you ahead of time that section 5.2 is a barrage of vocabulary, but I suppose you've already seen that now. So the last couple of definitions here. An Euler path. So we've already described what a path is. So an Euler path is a specific kind of path. First of all, it only happens in a connected graph anyway. So if you have a graph that's not connected, this definition doesn't make any sense. An Euler path is a path that traverses all the edges of the graph. So being a path, edges can only be traversed once. So an Euler path really means I've walked every single edge inside the graph and I did so once. Okay, I never retraced my steps along an edge. An Euler circuit is simply an Euler path that is a circuit. An Euler circuit is a path that travels through every edge of the connected graph once and only once, but since it's a circuit, you also return to where you started. So consider this graph right here. Start it at vertex C. Consider this walk. C to A to B, B to E, E to A to D, D to B, B back down to C, and then C to D. That's an Euler path. You walked every single edge in the graph, didn't you? You traversed every edge. And you did so exactly once. You never retraced your steps along an edge. Here's an Euler circuit for this graph. We start and end at C. So notice it's the same graph as this, except we add a triangle at the bottom. And it's the same path as this. We just now go from D to F and F back to C. So here's an example of an Euler circuit. Okay, in the graph over here, this graph has several Euler paths, and we found one of them. Okay, and you might want to start somewhere else. So if you want to, think about starting at D. Think about starting at A. Think about starting at B. Is it possible to find Euler paths wherever you start, wherever you feel like? Or are there only certain vertices where you can find such things? In this graph over here, we found an Euler circuit, but there are many of them. And you could ask the same question. Can I find an Euler circuit starting at D? You know, we started at C, but could I start at D? Could I start at A? Could I start at E? Etc. The graph below has neither an Euler path nor an Euler circuit. So let's think about what that means. Suppose I say, let's start here at A. I want you to walk every edge inside the path exactly once, and you can start and end wherever you feel like. So you say, okay, well, I'm starting at A, so maybe I'll go A to B, B to C, C to D, D to A. Okay, so I've walked the outer perimeter, and now I have to go right here, and oh no, I needed to traverse this edge also. All right, but now I can't do that without retracing my steps. So I've done this, this, and now to get to the other diagonal line, I have to go like this, or I have to go like this, and either way, I'm retracing steps. So that didn't work out, but maybe I could start at C and maybe go like, let's go diagonal first, and then like this. Okay, so sorry, let me show you again, like this, like a bow tie. Now I have the bottom edge and top edge left to walk. So I can walk the bottom edge just fine, but now to get to the top edge, I have to retrace my steps. So, you can play with this for a while, and it might not become clear until you've walked every possible path that there is no Euler path or Euler circuit. Okay, so that was, as I say, a barrage of vocabulary and terminology, but we now have all of the terminology in place to actually start solving some street routing problems in the next section. So sections 5.3 and 5.4 are dedicated to the questions of, here's this like neighborhood, or here's this sequence of bridges, or whatever, and I need to make deliveries along them, or I need to patrol them. How do I patrol them? What's the most efficient way to do that? Is there a most efficient way to do that? If so, can you tell me what it is? All the questions like this are what we will do in sections 5.3 and 5.4.